of heating metal to cherry red has been developed into an exacting science, employing modern instruments and new metallurgical knowledge. Muscle power has been multiplied and is now measured in tons of force which pound or squeeze all kinds of metals into a multitude of shapes. The development of modern transportation has been furthered by advances in forging techniques. In our conquest of the air, forging knowledge and new kinds of forging equipment are providing components essential to efficient progress. And now, as we reach out into space, we are more than ever dependent on knowledge of metals and the techniques for forging lighter and stronger materials, new and unusual metals with new and unusual processes, so that we may then become the blacksmith for the stars. For over 75 years, Wyman Gordon has pioneered in the forging industry. Experience, knowledge, and skill acquired since 1883 are combined with the latest in forging and scientific equipment to answer the forging problems of our atomic and satellite age, and to answer them today. In 1946, Wyman Gordon began operation of an 18,000-ton press for the Air Force in their North Grafton plant. This was the first of America's heavy presses to play a leading role in light metal forgings for aircraft. As the need for larger aircraft forgings became more evident, this 35,000-ton press was put into operation in 1955. This equipment provided a great increase in our country's capability for larger, stronger, and more intricate aircraft components. Six months later, even greater capability was provided in the 50,000-ton press. These heavy presses were originally built to produce larger and more massive forgings of light alloy material. Increasing challenge came with the rapid growth of our missile program. To withstand the shock and stress of takeoff and supersonic speeds, the eroding fire of propellants, and the incandescent heat of atmospheric re-entry required a new family of materials. Wyman Gordon was ready with an extensive research and development program and with manufacturing capabilities and experience to accomplish the development of these new forgings of new materials. Many components are already being forged for some of our well-known and successful missile and space vehicles. This missile nose component of beryllium is but one. Others include this dome forging of copper and a nose cone structure of magnesium. Components of aluminum and magnesium offer strength and light weight for the support of missile guidance systems. Many high-strength steel and titanium alloys are being forged today for rocket motor cases, such as these forward and aft closures for solid propellant motors. Motor nozzle housings of titanium alloys are forged to provide a high strength-to-weight ratio. Refractory metals, such as molybdenum and tungsten, are forged for other nozzle applications. Liquid propellant tank parts, such as this aluminum bowl, are being currently forged, as are the parts of this titanium pressure vessel. Turbine engine parts are forged in high-strength nickel base alloys, such as this wheel of Rene 41 and this machined one of Astroloy. Many other forgings are now being produced for the many missiles, rockets, and glide re-entry vehicles successfully proved and under development. And the list of metals includes magnesium, beryllium, aluminum, titanium, zirconium, steel, copper, columbium, tantalum, tungsten, and other nuclear and space materials. The ultimate product performance requires partnership of experienced forging engineers with the product designers from the beginning of design activity. Wyman Gordon engineers, together with the customer engineering personnel, study the geometry of this model section of the forward head on a rocket motor casing of a long-range ballistic missile. Here they work backwards from the finished piece to the raw material which they will need to forge it. They review together the performance required, the metallurgical properties, the tolerances, the location of bosses, the surface finish requirements, and other essential characteristics of eventual design. Machining requirements are studied in advance. Experienced forging engineers must take into account the character of the forging processes as well as the end product requirements in order to provide the most effective forging design. The forging die designer, with his knowledge of metal deformation, determines the forging steps required to produce the part as well as the most appropriate size and shape of the beginning raw stock. Specific die designs are worked out by development teams consisting of personnel from the laboratory, engineering, forge shop, and die shop. All requirements of the job are considered, such as forging temperatures and pressures for each operation, and the amount of heating required. The engineers determined that this part would require 2 forging steps. The first set of dies perform a preliminary operation. Then a second set of dies perform the finished forging, providing a part which has all of the structural and metallurgical properties required. Material at the rim of the bowl is removed for testing purposes, and the finished forging is machined to the required close tolerance. When missile engineers work with Wyman Gordon, from the research and development stages through to the final production, the best possible component can be produced, taking into account design requirements, material utilization, producibility, and total cost. But to provide dependable forgings, many related activities must be tied together. The laboratory constantly analyzes raw material to be certain it meets all specifications. Difficult performance specifications and the high cost of many of the new metals being forged today require extensive testing of both raw material and finished forging. Spectrography is one method used to determine the elements present in a material. By burning a sample and analyzing the light emitted, the direct reading spectrometer gives a permanent record of alloying or impurity elements. In addition to a chemical analysis to determine metal content, a sample is etched to check the macrostructure of the cast ingot or billet stock. Macro etching proves the absence of columnar grain, segregation of local areas of excessive alloying elements, metals or non-metallics, or porosity due to gas entrapped in the material. These checks also help indicate how the material should be worked in preliminary operations to avoid internal rupturing or lapse during forging. Here again, a macro etch sample from the finished forging helps to evaluate the success of the design in accomplishing the desired metal flow. Notice the concentration of grain flow lines in the area where maximum strength is desired. The electron microscope is a metallurgical development tool used to study and evaluate the effects of processing variations on the structure of materials. These electron micrographs of a titanium alloy with an original magnification of 12,500 times show the structure and alignment of aging precipitate. This uniform, fine, randomly oriented precipitate indicates proper working and heat treatment. While the raw material is being analyzed, carefully worked out die designs are turned over to the die department, where the forging dies are made by the most economical method. In some cases, a numerical tape-controlled machine is used for sinking the dies. Dies are also prepared by electric discharge machining, electrochemical milling, and other more common methods of metal removal. Now, going on to actual manufacture of the forging itself, all the planning by product designers and Wyman Gordon engineers moves into the production stage. The billet of high-strength alloy steel, which has been thoroughly analyzed by the Quality Control Laboratory, is cut to appropriate size of raw material. The mults of raw material are heated to optimum forging temperature in carefully controlled gas-fired furnaces. Next, the raw material goes to one of the large presses for the first forging operation. Metallurgists and engineers decided on 2 closed die forging operations for this part because of the large amount of material movement. When larger production runs are forged, material handling equipment is used to expedite the flow of work from furnaces to the presses. After a dimensional spot check, the piece is returned to the furnace for further heating for the finished forging operation. In this operation, material movement is completed so that all areas are filled and the final forging dimensions are achieved. As the piece comes out of the press, it is given a preliminary dimensional check. After the forging has cooled and been cleaned, it will be carefully inspected to be sure all geometrical relationships have been met, that web and wall thickness have been maintained, and that sufficient material is available for an integral test. To attain the desired metallurgical and mechanical properties in the finished part, each forging is subjected to a carefully controlled heat treating cycle. Wyman Gordon maintains extensive facilities for the machining of forgings. In many cases, machining is necessary during various stages of the forging process to assure optimum mechanical properties. In other cases, complete machining is a service to the customer, as well as a further guarantee of the finished part's quality. One of the machining operations is the cutting off of the extra material which the engineers included for an integral test piece. This will be cut up for tensile and stress rupture testing. Here, the machining of the dome-shaped contours of this missile closure is accomplished by a duplicating machine. A tracer follows the contours of the model and controls the milling cutter so as to reproduce the same contour on the finished forging. In this case, a vertical boring mill has been adapted to turn the contours around the bosses. The part is mounted on a rotating table, and the cutting tool holder moves up and down, controlled by a cam and roller, the cam being designed to produce the desired contours. After machining, the parts are subjected to rigorous product inspection. This is a vidigauge, a direct reading ultrasonic resonance method of measuring wall thickness from one side. The reflection of sound waves from the first surface is indicated on the screen by the blip on the left, and the back surface reflection is indicated by the blip on the right. The distance between the two is a measure of the thickness of the part. The condition of the machine surfaces is also checked with the profilometer to be sure the micro-inch finish meets specifications. Many forgings are given a sonic inspection to check internal soundness. The part is immersed in water while ultrasonic waves are transmitted through the part. If there are any mechanical discontinuities, voids, or inclusions within the forging, they will change the pattern of the waves reflected back to the screen. Many forgings receive Zyglow inspection for possible surface defects. The forgings are immersed in a fluorescent penetrant which finds its way into minute cracks or laps in the surface. After the forgings have been washed and dried, they are examined under ultraviolet light. Certain forgings are given a radiographic or X-ray examination. Wyman Gordon is continually searching for new and better materials and techniques to meet the challenge of the space age. One of the contributions of this program is the development of metallurgically sound, uniform, and stable materials. A complete induction vacuum melt facility makes possible the limited production of carefully controlled alloys. Basic metals can be accurately combined to provide forging ingots of super-strength steels, nickel base, cobalt base, and other heat-resistant alloys. Thus, the Research and Development Group can experimentally forge materials prepared to their own formulation and evaluate the results of using metals and alloys that are otherwise unavailable. Our nation's success in the space age in overcoming the problems of stress and heat, of launching and re-entry, may well come from research effort such as this. Extensive effort is being expended to produce domes and closures of titanium alloys by closed die forging. The cryogenic properties of this material, with its high strength-to-weight ratio, provide reliable forgings which are resistant to corrosion and thermal shock. Alloy steels offer high strength when forged into domes and closures for solid propellant motor casings or liquid propellant tanks. The complex stresses of this type of closure call for a high strength-to-weight ratio. Forgings of these materials have proven reliability. Turbine wheels for liquid propellant systems are another critical requirement successfully met with special nickel-base alloys. These materials are continually being evaluated and have been successfully forged into turbine wheels up to 50 inches in diameter and into closures up to 65 inches. Many other forging development programs are underway for other materials such as tungsten, tantalum, molybdenum, and columbium. This 1,300-pound ingot of columbium is being pancaked for forging into a bowl. Special coatings are employed to insulate, lubricate, and prevent contamination during the forging process. Nozzle liners and throat inserts for rocket motor nozzle bodies are currently being hammer forged of molybdenum. Experience is proving that forged components of refractory materials such as this have outstanding reliability and resistance to erosion and thermal shock. Other manufacturing capabilities include ring rolling of various alloys. Wyman Gordon equipment and personnel cover a wide range of facilities and experience to produce the greatest number and largest variety of forgings for aircraft and missiles. In its Worcester, Massachusetts plant, Wyman Gordon operates a wide variety of press and hammer equipment. At Harvey, Illinois, is a plant specializing in crankshafts with facilities to produce a variety of other forgings as well. At North Grafton, Massachusetts, are 11 presses ranging from 600 to 50,000 tons in a facility built by the United States Air Force and operated by Wyman Gordon. The combined capabilities, experience, and facilities of the entire organization are available to produce missile components in closed die and hammer forgings from any workable metal. Our team of sales engineers, metallurgists, and product engineers are available to help solve missile and vehicle problems from research and development stages through to the final machining of components. Experience, knowledge, and skills of over 75 years as pioneers in forging are combined to develop answers to man's conquest of space as Wyman Gordon becomes the blacksmith for the stars.